So welcome all of you. This is Basecamp version 8. This is something that we have been doing at the Starknet Foundation for a while. Not only those, we only also have people from the community doing their own Basecamp sessions in different parts of the world. So first of all, what is Basecamp? Okay, so as I mentioned, Basecamp is a way to onboard developers to the Starknet ecosystem. So at the beginning, we're going to start with more generic, more fundamentals that anyone who is even not a developer will benefit from it. But eventually, we're going to transition to more hands-on, more technical content that for sure are going to be interesting for developers, for architects, and the like. This iteration of Basecamp is going to be a 4-week course taught live over Zoom. We also are live on YouTube as well right now. As you know, it's going to be 2 hours each session. Join the Discord server. We're going to have soon a Basecamp channel there and on the Starknet Discord, but that will be the place for you to ask questions, especially for the homework. If you get stuck, that's a place to have discussion, either with me, with Omar, or with your peers, also trying to solve the homework. And also join the YouTube channel from the Starknet Foundation, because that's a place that we're going to post the recordings of all the sessions. Right now, we're streaming live, but as soon as the streaming ends, it's just going to be available as a recording for you. And as I mentioned, we have 4 sessions for this course. Today is session 1. It's about fundamentals. Session 2 next week is going to be deep dive. We're going to go deeper into things like architecture, recursion. Then we're going to talk about Cairo, in this case, vanilla Cairo. And then finally, we're going to focus on Starknet and smart contracts using Cairo. So before we start, I like to first clarify the different names that you might find in the ecosystem. So you probably know what Starknet is, right? But I don't know if you know about Starkware. And Starkware is actually the company who developed the technology that powers Starknet. And this is a company that is based in Israel. And the first product that they actually created was not a Starknet, was Starkex. And a Starkex is what's called a layer 2 Validium. It's not a rollup. That also uses ZK proofs. Very similar tech stack to Starknet, but the main difference is that Starkex is a permission system, right? Not anyone can go and deploy their logic, their smart contracts. Actually, it doesn't support smart contracts. But Starkex is the technology that actually powers DYDX version 3, Immutable X, Sorare, and apps like that. And then more recent is that when Starkware took this technology and they say, hi, what do we make like an open system where people can deploy smart contracts? And it's not going to be permission. It's going to be permissionless, and that is, of course, is a Starknet. So a Starknet is a proper layer 2 rollup using validity proofs, using the same technology pioneered by Starkware. Actually, one of the co-founders of Starkware is the cryptographer who came up with the ZK Starks. We're going to talk later. That is the underpinnings of the validity proof that we use on Starknet, and that actually other protocols are using as well. Finally, we have the Starknet Foundation. It's a non-profit organization that I think has been alive for about a year. So the Starknet Foundation, its goal is to be like a credible, neutral entity whose goal is to promote Starknet, to help it grow, help with the governance as well. So that Omar and I actually work for the Starknet Foundation. So that you have it. You have Starkware, Starkex, Starknet, and the Starknet Foundation. So with that out of the way, we can actually start with the session 1 fundamentals for today's Basecamp. The topics for this session is, first of all, we're going to talk about why Cairo, why we came up with this particular technology. Then we're going to talk about Starknet, why actually we create this new layer 2. Then we're going to talk about smart wallets, which is one of the most interesting topics when it comes to UX. That is only possible thanks to things like account abstraction. All right, so why Cairo? I'd like to explain the reason of Cairo with an example or a story. Imagine you're the head of an agency whose goal is to do space exploration, right? Your goal is to send a small spacecraft to Mars for observation. And of course, to launch this spacecraft, you have to do some important calculations in order to save fuel as you can. For example, you need to know what is the best launch window. So the planets are going to be as close as possible. What is going to be the best trajectory? So, not only is closer, but maybe you can save some fuel by using some gravity or whatever. But these computations are complex, right? You will need to create some kind of algorithm to calculate those variables. So maybe you can actually delegate to your engineers, say, hey, can you come up with a program that actually calculate these 2 important variables? And your engineers might actually choose to use a very high performance language like Rust or C++ to try to get the answer as soon as possible. So of course, eventually they come up with a program. Let's say in this case, it's written in Rust, but they have an issue, right? This calculation is so complex that you need a supercomputer to actually get the answer in a reasonable amount of time. But you don't have a supercomputer at hand. And because your space exploration agency is not big enough, you don't have a budget to get one. So your only option really is to collaborate with a rival country that actually has one supercomputer and that has agreed to actually execute the program for you and give you the answer. So maybe you get to an agreement with them to say, okay, sure, I'll give you my program, right? You will execute it in your country, and then eventually you will give me the answer, the result. But there's an issue, right? When you get the result, how do you know if the supercomputer didn't malfunction while executing the program? Or how do you know that, for example, a rival spy agency did some sabotage, just even a small change in the computation, so completely derail your space program? So you wouldn't really know, right? You only get the result, but you don't know if it's actually the output of your program. You have to trust that this rival country has done the right thing. So that is the issue with a language like Rust, like C++, like any normal programming language. The only way for you to verify that result is true is to take another machine, re-execute the program, and compare results. And maybe you need to do that multiple times to get some kind of consensus of a majority. And that is exactly what Ethereum does, but it's not very efficient. And in your case, it's not possible. Now, imagine that instead of writing the program using Rust, you will write it using Cairo. Now you will give them, again, the program for them to execute. But now when they get back to you, not only they give you the result, they also give you a proof that attests of the integrity of the computation. You can take that proof and with your laptop, in this case with some commodity hardware, you can actually verify that the output is actually the result of executing your program. So with the validity proof, if the execution is intentionally or unintentionally modified, the proof will be invalid and you will know it right away. So in other words, what Cairo allows you is for a regular computer to keep a supercomputer honest. And that is a superpower that this technology enables. And that is one reason why we use it for Starknet, as you're going to see later on. So this is, as you can see, is like a new generation of programming languages that had this weird property that you can prove the execution of a program written in this language. Another use case or a scenario where you will want to use Cairo is like, imagine that you're in a company and one day your boss say, hey, what if we have our own, machine learning model that's gonna make us gain a lot of money and be different from, and maybe they give you the task to you and you say, well, actually, that's actually possible because we have a lot of internal valuable data in the company that is private. And there are some open source models that we can actually use like Llama or whatever. So that's doable, right? We can do that. But again, the problem is that doing this training is actually very consuming in terms of computing power. You don't have that kind of power at hand to do the training yourself. So what you will need to do is that actually you hire a third party, company B, that they actually specialize in training models. You will give them your private data, right? They will train the model using something like Python or whatever language is used these days for AI, and they will give you back a model that is now trained with your data. You got back to the same issue, right? Like, how do you know if this model that you're getting back was actually trained with your data? Maybe it was trained only partially with your data, and they actually try to save money by not using all the data for training. Like, you don't know until you use the model over and over and to start to see some limitations. So you have to trust that they're actually doing the training correctly for you. Now, if they actually used Cairo to train the model, same benefit, right? You will get the model back, but also you get the validity proof that the training was done as you wanted, exactly with the data you provided. You will know it right away because you can verify that proof independently. And if they didn't do the job that you asked them to do, you will know right away because the proof will be invalid. That's another interesting use case, especially for these days in machine. Now, some of the Kairos feature, as I mentioned before, it creates what's called provable programs, a program where you can prove the execution. It runs on top of the Cairo virtual machine. And this is reason why Starknet is not EVM compatible. It's because we have our own virtual machine called the Cairo VM that is especially for these type of programs. The syntax of the language is inspired by Rust. So if you have any knowledge of Rust, you are like a 90% there to be proficient with Cairo as well. They have some small differences here and there. But things that are similar is, for example, the ownership model. of Rust, you will find it as well in Cairo. Similar as in Rust, Cairo is a strongly typed language. It uses traits, so you don't have inheritance, as in the case of Solidity, for example. And you also have macros to do what's called the meta programming, which is also a superpower of Rust. You have it also on Cairo as well. And another interesting feature is that you can actually use Cairo for anything, right? You can use it on a Starknet for sure, but you can use it also on its own. It's a general purpose programming language. And that's also an interesting feature that is going to enable a whole, field of different applications that are going to be possible thanks to Cairo as part of a Starknet or outside of a Starknet. And one of the best things, in my opinion, is that even though the whole language in the stack is optimized to use CK circuits, you don't need to know anything about CK as a developer to actually use Cairo. It does a very good job as abstracting away all that complexity, so you can just focus on your program. To give you some taste of how Cairo actually looks like as a programming language, this is how you will define a custom data type, in this case, a rectangle. You will use a struct. You will define the properties, in this case, scalar types. This is very similar to Rust. This is how you will define like the interface using traits. Here I define two different functions or two different methods. They get the same. The first argument is going to be self. Then you define what it returns. So basically, this is how you define the blueprint of this custom type. Again, this is same as Rust. And then you have the implementation of that trait, right? I believe this is a bit different now from Rust, if I'm not mistaken, but people who know Rust better than me, let me know. And here's basically the body of the functions that we define in the trait, right? So just for you to have a sneak peek for now, we have a session dedicated for Cairo, session 3. But at least you have some idea how it looks like and why we say that it's similar in syntax to Rust. Important is only similar to syntax. The compiler that Cairo uses is a completely different compiler from the Rust compiler, because the target machine is not a regular computer, it's the Cairo VM, which is like an abstract computer fine-tuned for CK proofs. So actually, it uses CK circuits under the hood. Now, when you want to create a smart contract for a Starknet using Cairo, then you will define your smart contract will be a module that has a special attribute, in this case, the Starknet contract. This is what I call the meta programming using macros. Then the storage of the smart contract is defined with a struct, also using the attribute storage. Then each of the properties you define will be the storage of your smart contract. Then you will define the public interface of the smart contract using a trait. You can see that we use this particular attribute interface. And you can see that I have here two very basic functions, set and get. Whenever you have a function that actually modifies the internal state, notice that it's based on what's called a generic. We're going to talk more about that when we go to the Cairo section, but just for you to have an idea of how a smart contract looks like, it requires a generic, it's the contract state. And then when you want to modify the state, you have it passed as a reference, so you can modify it. When you only want to read from the state, you get it as a snapshot, which is like an immutable view of the state. You cannot modify. This is a way for the compiler to help you out. Like if you're trying to write a view-only function and you pass a snapshot and you by mistake, you try to write to the state, the compiler will tell you, hey, you're trying to do something that is you didn't want to do initially, right? You're violating the contract. People asking the Q&A. Okay, Omar, you're on it. Good. Yep. All right, so now that we have a trait, we actually have to implement that trait in the smart contract. Right? And that's where we say, okay, we have an implementation. This is the body. So when we want to set the value, not only we need the state, we also need which value, which is going to be passed by the user. And then this is how you call the storage and actually write the value, right? Look at the stored data. Is what we have here in the storage. We use the method write, and we want to read. We use the same method read. Notice that same as Rust, when you don't have a semicolon at the end, it means that you are returning the value directly. To summarize, why Cairo? As I mentioned, it creates what's called provable programs. It gives you the proof of the computational integrity, so you know that the output is actually the result of executing your program. It allows you to verify it without having to re-execute the program, right? Which was the initial problem I described with the space exploration. Like if you didn't have Cairo, the only way that the result is correct is to re-execute in different computers and compare the result. Cairo has also a very powerful and flexible language, which if you appreciate Rust, you will appreciate Cairo as well. And it helps you prevent cheating and malfunction, which is also interesting that even if the hardware fails, you will know it. And in summary, it keeps a supercomputer honest. Okay, Sahar has a question. Does a Cairo program, which is a provable program, can generate an under constraint proof? I don't think so, because Cairo is a high-level language. So the proving part, all of the thing is abstracted away from you. You don't have to take care of the constraints, because actually the Cairo CPU is the one to define the constraints for every single simple operation that it performs, the I/O. So I would say no, but I can tell you for sure, because maybe you're going too deep into the architecture. But for the most part, anything you can execute with Cairo program is going to be proven, or you can prove it actually, and then you can verify it. And you don't have to know anything about CK for that regard. So someone's asking, so Cairo is general purpose programming language, not only to write smart contract on a Starknet. Yes, that's correct. You can use Cairo on its own. I'll call it vanilla Cairo. And that's actually been used for different projects. For example, Zero Sync is the one that always comes to mind. And maybe I can show you here. You can find it. Zero Sync Bitcoin. This is my go-to example of using Cairo in a completely different environment that is not a Starknet. And basically what they do, this thing here, is they allow you to sync a Bitcoin node in minutes, just by verifying a validity proof of the generation of the UTXO of a Bitcoin node, right? So you can trustlessly sync a Bitcoin node in minutes instead of multiple days or a week. That's one example. Herodotus is another example using storage proofs. Yeah, so again, it opens a whole new space or design space for new applications that can be implemented as smart contracts on a Starknet, or can be implemented just on its own in a completely different environment. So we talk about why Cairo. Now let's answer the same question, but for a Starknet. Why did we actually create Starknet? Actually, when we say we, it actually was Starkware who created the Starknet. We have to start just thinking about what is the issue we have right now on Ethereum, the scaling problem. And on Ethereum, you have what's called the block producer, which is the block that gets the chance to propose a new block by staking some ETH. So this node actually proposes a new state of the network. Let's say the state is 42, and propagate the state to the Ethereum network, right? So all the other nodes in the network, all the validators on the Ethereum network, will take this proposal of the new state, this new block. And what they're going to do is actually going to re-execute all the transactions on this proposed block and validate that they actually get to the same global state, right? That they get the same 42 in this example. So you can see this is very robust, because if a block producer tries to cheat, if the majority of the validators are honest, they will be able to detect that inconsistency, right? And say, hey, this block is invalid. Actually, you're cheating and you're going to get slashed. But you can see that even a small transaction gets re-executed over and over tens of thousands of computers all over the world, which is not very efficient when you think about the system as a whole. In the case of a Starknet, when the Starknet proposes a new block, in this case, it's a layer 2 block, right? Starknet doesn't propose blocks on layer 1, but it proposes a new block on layer 2, say, hey, this is the new state, this is all the transactions. Sorry, it doesn't give you the transactions, only tells you what is the new state, and also gives you the validity proof, right, of the execution to get to the result. That validity proof is sent to layer 1, so now all the Ethereum nodes can actually verify that proof. And the verification of the proof is only a fraction of the effort what was required to actually execute all the transactions at number 42. And they will have certainty that that's the actual valid result. You can see the effort done by Starknet is a little bit over than just executing the transactions, because on top of the computation, it needs to calculate or generate the validity proof, right? That it requires additional computation. But the benefit is that the system as a whole is much more performant, because now it's not like every single node on Ethereum has to execute every single transaction to get to the same result. They only have to verify the validity proof, and that will be enough for them to trust or to be or to use it as the attestation of the result of the new block. So now you executed once, but you verified everywhere. We have a question here for Marshall. I am completely a newbie. Is this something I can learn and create something? I really like what Starknet is doing and would like to be a future developer on Starknet. We have a lot of resources to learn. Maybe Omar, you can share some of the resources. Maybe if I can share now, Basecamp is a great place to start to learn. But if you want to go deeper into, for example, Cairo as a programming language, the Cairo book is a great resource. I'm gonna put it here in the chat. And then you also have the Starknet book as well. So those two resources are complementary to what you're gonna learn here today during Basecamp. Nathan is asking, is there any actual rollback or correction on the Starknet if a block has been added to the Starknet blockchain, but the submitted proof is considered invalid by mainnet? Yes, in that case, we're gonna have some reordering, right? Like it will be the same as if in layer one a block producer proposes a faulty block, you will have some reorg. All right. So the point I was making here is that the effort done by all the validators on the Ethereum network is only a fraction what is required to get to the same result, the global state on layer two. But now to the question, when I say a fraction, what do I really mean by a fraction? Well, if the effort done by the sequencer to calculate this new global state on layer two is X, for example, it took X steps or X cycles, the effort of a single validator to verify the associated validity proof of that execution is polylogarithmic, right? This is log square of X, and this is a log base 2. Maybe it's easier to see it in a chart. You can see here that the X-axis will be the number of steps required to compute a new layer 2 block, while the Y-axis will be the number of steps required to have certain output. In the case of the sequencer, it's obviously linear, right? It's the calculation requires 100 steps. The sequencer needs to do 100 steps. But in the case of the validators, they only have to do log square of X. In this case, will be if the sequencer did 100 steps to get to the new block, each Ethereum node will only do 40 steps. Right? And this is just an example, obviously, because the bigger the block, the more computation is required to derive the state. The bigger is going to be this difference, right, between these two lines. So that's what we're gaining in performance. That's a type of compression you're going to see. And this is just the base case, right? This is without considering what's called proof recursion that greatly improves this chart. It actually makes it more separate these two lines, much more performance. Yeah, Pablo asked, could you explain the proof recursion concept? That's going to be explained in session 2 next week. So let's wait for that one. All right. So the point that I want to make here is that validity proof is a type of compression, right? The same way that the zip algorithm is a way to compress file size, validity proof is a way to compress computation. That's why we say we actually improve the performance through validity proof of the network. So going deeper into validity proof are a use case of zero knowledge proofs. And the idea is that it convinces a verifier on layer 1, and this verifier is actually a Solidity smart contract on Ethereum, that a new layer 2 state is real, or a particular new layer state, without having to share all the transaction details, right? Which I think when you see something like Optimism and Arbitrum, they actually have to send the layer 2 transaction details to layer 1 because they need to allow for the person submitting the fraud proof to re-execute transactions. In the case of a Starknet, you don't need to share the details of the layer 2 transactions for the verification of the proof. Now, this doesn't make layer 2 transactions private, even though we don't send them to layer 1. And doesn't make them private is because Starknet is an open ledger, right? The same way that Ethereum is. So you can very easily, maybe not easily, but it's possible to connect the dots, say, oh, these proofs come from this block, and this block all the transactions, so you know exactly what happened. So we use these properties of zero knowledge proofs is to make verification very efficient, right? Not for privacy. So because we use validity proofs, we like to call Starknet a validity rollup instead of a ZK rollup, just because ZK people assume that there's some privacy preserving system, which is not, right? So you can call it ZK rollup if you want, but we prefer the validity rollup just to make the distinction that it's not about privacy, it's about being efficient in the verification. Starknet in particular uses a type of zero knowledge proofs called Starks, which is different from the Snarks. This is kind of a debate, what's the difference between Starks and Snarks, but we like to stick to it that Starks is a different family of validity proof, different from Snarks. And what it allows you, Starks, is that you get very efficient proving and verification as well. What's the difference between the T and the N in Stark? I think the T is for transparent, scalable, transparent arguments of knowledge. I think that's what it means. I forgot what Stark meant. But is the scalability of Stark superior to all private CK proofs like Snarks? Example, log square scaling better than Snarks? I think this slide is gonna answer the question, at least from the point of view that I see it, me not being a cryptographer. But at a very high level, when you compare Stark versus Snarks, the verification is, as I mentioned in Stark, is polylogarithmic, right? It is the curve that I showed you before, is this curve that we have here, right? In the case of Snarks, it's actually constant, right? So it doesn't depend on how complex the underlying computation is. It's always the same. The proof that is sent to layer 1 for verification in the case of Stark is in the around 400 kilobytes. In the case of Snark, is very small. It's like 300 bytes only. So you will think, wow, well, Snark seems to be much better than Stark. Like, why did we bother to actually use Starks as a foundation for Starknet? And the reason for that is this properties here. First of all, proving is an order of magnitude more efficient with Stark than with Snark. There's not a lot of discussion about proving efficiency these days, just because all these systems at this point are centralized. They're single prover. So up until the point that we try to decentralize the network, no one's going to really care, but it's going to be really important to try to decrease the specs as much as possible, because proving is a very CPU or memory intensive computation. So Stark is very efficient in that regard. They're also easily parallelizable, the proving, which I think is not the case for Snark. Another advantage is that with Stark, you don't need a trusted setup, which you need for Snark. This trusted setup is basically to come up with a secret that the prover and the verifier know, and no one else know, and make sure that the secret doesn't leak, because if the secret leaks, the system can get compromised. So on a Stark, you don't have that issue, right? So I think there's no toxic waste, as Ellie Benson likes to say when talking about Starks. And also another nice benefit is that the Starks are still deemed to be quantum secure, while the Snarks are not. So, quantum computers are coming at some point, and when they become sufficiently powerful, they're going to be able to break many things. One of the things will be the Snark proofs. They're going to be able to submit fake proofs that look like valid, that they pass the verification. In the case of a Stark, they're still deemed to be quantum secure, mostly because the only cryptographic primitive used by Starks is hash functions. The rest are just polynomials. It's just polynomial. Hash functions and polynomials. That's why it's considered to be quantum secure. And the reason is because anything that is similar to elliptic curves, we know there is an algorithm using quantum computer to actually break it in a reasonable amount of time. People usually ask us, okay, so why Starknet is not EVM compatible, right? Why are we not a CK EVM? And the reason is because there's a trade-off that you're making, right? If you're making a system that is CK EVM, sure, you're using CK proof. You can also use Starks if you want to. You will gain compatibility because technically you will be able to deploy most of the Solidity smart contracts directly on your layer 2. While if you use your own custom virtual machine like the Cairo VM, you wouldn't, right? You just can deploy a Solidity smart contract to Starknet. It wouldn't work. You have to rewrite it in Cairo. But what you gain by focusing on a virtual machine that is custom made for CK proofs is that you get performance, right? We are able to extract the maximum performance of the system. And this is mostly thinking long-term, right? If you're gonna get crazy, try to push the technology to the max, we might as well just go all in and try to have something that is fine-tuned for this new paradigm of CK proofs, right? So we sacrifice compatibility, but we gain in performance, especially in the long term. Vitalik famously, he had a blog post classifying the different CK EVMs into 4 different categories. So he mentioned that, okay, the type 1 CK EVM is one that you can deploy any Solidity smart contract as it is directly on this new layer 2, and it will work. The downside is that it will be very slow because the EVM was conceptualized as a traditional CPU architecture, right? Not a CK circuit. So there are things that for a traditional CPU in this new paradigm, or trying to migrate that into a CK circuit, is not efficient at all. To my knowledge, there are no projects right now that are able to claim to be a type 1 CKEVM. Now, CKEVMs type 2, they have very high compatibility, but not full compatibility because this new intermediate virtual machine will have some changes in how this, for example, the storage data structure. The performance will still be slow, not as slow as before, but still slow. But again, to my knowledge, there are no projects right now trying to tackle today type 2 CKEVM. When we get to type 3 CKEVM, we now start to see projects, right? The compatibility of the Solidity smart contracts now it's partial because now there are changes on storage data structure, on the type of hashes being used, some of the pre-compiles. The performance now is better, right? And here's where you see things like zkSync, Scroll, Polygon CKEVM. You also see Kakarot, which is interesting enough. Kakarot is a project built with, it's actually building EVM bytecode to Cairo VM transpiler. What that would allow you is to actually deploy Solidity smart contracts as a layer 3 on top of Starknet, and it will work. It will work using the Cairo VM under the hood with all the benefits that you get out of that. Finally, you get the type 4 CKEVM, and the idea here is that they have a completely different virtual machine, unique. So they're not compatible with Solidity smart contracts. The benefit is that they're very fast. That's where Starknet sits right now. Polygon mining is also targeting the 4 CKVM. I also put here Aztec just because I know they have a different VM, although they are making probably different trade-offs because they're focusing on privacy, which is not the focus for Starknet or Polygon mining or any of the other CKVMs out there. So I still don't know exactly what are the trade-offs they have to make, but they have a different VM, so they are considered type 4 CKEVM as well.
There was a question regarding if we would be able to deploy Viper contracts on a Starnet using, well, Viper contracts using Kakarot.
I imagine because Viper, at the end, it will compile to the EVM bytecode, right? So Kakarot takes EVM bytecode and just turn it on the fly to Cairo VM. Not on the fly, when you deploy it, it will turn it into Cairo VM bytecode. So yes, technically, you will be able to use all the tooling that you can use for Solidity, for Ethereum, directly on Kakarot as a layer 3 on Stargate. I don't know if there's a website to track progress. Omar, do you know if Kakarot has some website that we can share?
Their GitHub repo is, I think, would be the most reliable source.
Oh, there's a kakarot.org. So if you want to learn more, put it here in the chat. Kakarot. There you go. If you like Dragon Ball, there you go. You will like Kakarot.
There's another question. Can you migrate a Solidity contract from type 1 to type 4 EVM?
This type of classification is for systems, right? Not for a smart contract. I don't know if you understand the question. Can you migrate Solidity smart contract? Oh, well, we used to have, for example, the opposite, right? How do we go from type 4? Like, how do you go from Cairo to Solidity? We used to have a compiler called Warp, but I don't think that's your question.
It was the other way around. But I think you can have any smart contract that you can deploy on any of these. You can have a Solidity smart contract and you can deploy it in any of these different EVM types. No problem.
Yeah. The type 1 is still as a pipe dream. I don't know if ever the Ethereum Foundation will try to tackle that directly. I
think Scroll plus Tyco might be working towards that.
Okay.
But again, as you mentioned before, there's a lot of trade-offs there, right? Either compatibility or efficiency.
Someone's asking, is Kakarot a layer 2 or layer 3? To my knowledge, their goal is to be layer 3, but we're going to have to wait until they deploy to know it for sure.
They're using Madara, the Madara stack with nodes.
I say soon nodes, available on Starknet L2 and L3. So apparently it can be both.
Now the question would be, David, do you think that transactions will be cheaper on Kakarot or directly on the Starknet layer 2?
Oh, that's a great question. I will say that I will bet that still cheaper will be on it.
I would chip that
because it will depend how efficient that conversion to bytecode is. But I don't know. you will have to wait until we have some benchmarks. But thinking out loud, I still think probably Starknet will be a little bit more performance. But hey, you don't have
Maybe
to rewrite your app, your smart contract. Oh, why do Kakarot team develop their own sequencer? That's a good question. Omar, do you have some answers to that one?
did they? Are you sure? I am asking the.
No, but
I
they
think
use
they're
Madara,
using the
right?
Madara. Yes, they're using Madaras. As long as I know, they're using Madara, but maybe the anonymous
So
attendee can provide more
yeah, so
information.
Kakarot didn't develop Madara, which is like this sequencer, but they're using it. And why they're using it, they like to explore. It's like it's important to have client diversity in different layers of the stack, right? So having a second type of sequencer, because Madara is built upon Polkadot's, I forgot the layer, foundation layer, but it's based on some Polkadot code as well, substrate. So it's always possible to
Yes,
have multiple implementations of different layers of the network. In this case, we're going to have more than one sequencer that you can use.
there are at least 3 different sequencers being developed right now from
What's the other
different
one?
parts of the community.
Oh,
We have the the one developed by Lambda class. I don't remember the name exactly, but I will send you the link to the Starnet book
we have
chapter where
Katana
we
as well,
review
right?
them. We have Katana, yes. So
Katana is a
sequencers can
third
have.
sequencer as well, but it's going to be, but yeah, it's available. Actually, you can use it as a test network if you want today as type of ganache, but it can be used in production as well in the future as a sequencer. The sequencer is a piece of infrastructure that is not too complicated because the only thing the sequencer does is to collect transactions, to order them, and to execute them. It doesn't really do anything about the proving side. So that's why it's a little easier to replicate having different implementations than having multiple different provers. That's going to be more challenging. But we actually have multiple different provers, actually.
We have at least 3 different, yes.
Yeah. Talking about finality on L1, and by finality on layer 1, I mean, how long would it take in the case of layer 2s for withdrawing assets from layer 1, from layer 2 to layer 1? Finality of Ethereum itself is about 6 minutes. When you talk about optimistic rollups, if you want to withdraw asset from layer 2 to layer 1, it takes you about a week, more or less. In the case of a Starknet right now, it's about 2 hours. That's the frequency. That's how often Starknet is submitting new validity proofs to layer 1 to secure the network. If you're thinking about finality at layer 2 directly, it's very fast. It's about 3 seconds. That's the time that it takes from the transaction to reach the signature and to be executed. Not proven, just executed. If you're going to wait until it gets proven and the proof get verified on the Starknet, it's about 2 hours. That's why for withdrawing assets, you have to wait that long unless you use some kind of service that they manage the risk for you. Anonymous asks, do they all settle on the same L1 contract? Or do new sequencers require new L1 verifier contracts? It will depend on which prover they're going to use, because as I mentioned, the sequencer doesn't do any proving. You just order and batches transactions. It's actually possible that different sequencers might use the same prover, it's called Sharp, the one that Starknet uses. So if that's the case, they will use the same L1 verifier. Anonymous is asking, what is the work within that 2 hours that is taking most amount of time? Proof generation, or does the prover wait for enough transactions to be collected to be more efficient? Yes, it's the latter. To make transactions as cheap as possible on layer 2, we batch as many transactions as possible, in this case, as many blocks as possible. And then Sharp, which is the system that created the proof, not only serves the Starknet, it also serves the Starknet. So it also collects all these operations on StarkX, on Starknet, combine them using proof recursion that we're going to see next week, and creates a single proof for all of them, the execution of all those transactions, settle that on layer 1, and now the cost can be spread out across many transactions, so it makes it cheaper. So actually this 2 hours is configurable as well, right? Anonymous says, so in the future, if the traffic increases, the finality time will be reduced. Potentially, yes. It was bigger before. It was like 8 to 10 hours, like a year ago. Now it's 2 hours. So yes, as long as it makes economic changes. Mm-hmm.
It's worth mentioning that this is L1 finality, but we also have L2 finality, which is very, very fast. And I think it's something we will review in the next session, right? Maybe.
Yeah. But right now, when you use, for example, Bravos or Argent X to send, let's say, ETH to another account on Starknet, you get confirmation in 3 seconds. Like it's super. It's also a result of we have a single sequencer, right? So it's very easy to get this fast. There's no consensus protocol layer 2. There's no need, right? The security comes from ZK proofs, not for consensus or having multiple sequencers. It's more like for preventing people from being, not able to use the system for whatever reason. We'll say, so L1 finality is only important when I'm bridging out. Yes, it's important for that. It's also important if you care about the maximum level of security that the network can give you, because L2 finality, it only tells you that, yes, the sequencer got your transaction, it got executed, but you kind of have to trust the Starkware because they control the sequencer. If you have complete, certainty, you better wait for the proof to arrive to layer 1 to be verified independently. So it's a matter of taste, right? It's like in Bitcoin, you can consider one confirmation to be enough, or you can consider 6 to be enough. It depends on your security threshold. All right, back to the slides. If you go to one of the block explorers that we have for Starknet, one of Starkscan, you can see performance of the network over time. And you will be able to see that the peak performance was 47.29 TPS. And this is deceiving because on a Starknet, every single wallet is actually a smart wallet. It uses a kind of abstraction. And for that reason, you can actually bundle multiple user operations in a single transaction. So what on Ethereum could be 3 or 4 transactions, you can actually bundle them on a single transaction on a Starknet, and they will count as just one transaction, right? Even though internally it could be 10, 20, 50. But 47 is the metric that you can see as the maximum. Now, if you look at the user operation, which for me is a more realistic way to measure efficiency of a Starknet, because actually it takes into account this multi-call, the peak that we got is 238 user operations per second. And this is a system that has a ton of optimization still in the pipeline to be implemented. If you want to see where I got these stats, you can actually go, for example, I got this one from Starkscan. I'm going to share the link. This is for testnet. Let me go to mainnet. I'm going to put in the chat. If you go to this section, you can see all these stats here, either on a Starkscan or you can see it on Voyager as well. That's another block explorer for Starknet. I put the link here. So we have 2 main block explorers, and they also share you some very nice statistics about the network. You can check it out. So to summarize this section about why Starknet, first of all, is optimized for ZK technology, which gives you more computer power, paying less in gas fees, because I mentioned that the cost of the proof verification is spread out among multiple transactions. It is secured by ZK Starks plus the Ethereum network, because that's where we post validity proofs. It has a very powerful programming language in Cairo, and it has a battle-tested tech stack. Like Starknet has been on mainnet for like 2 years. And as I mentioned, the same technology, same validity proofs are used for secure StarkX. And if you know anything about DYDX, they do a lot of transactions and they move a lot of money. So this technology has helped secure about $1 trillion in transactions across all these systems served by the same prover. I have to update these slides. The finality is not 10 hours, it's 2 hours now.
Yes, plus also mentioning that all the companies on top of StarkX, for example, DYDX, Sorare, Immutable, Reno5, and so on, they are all using Cairo behind the scenes. So Cairo is securing a higher amount of...
That's a great point. If you go to L2 bit, you're going to see that if you see this symbol, this is the symbol of a Starkware. It's actually a system using StarkX. So you see DYDX version 3, Immutable X. Who else we have here? Apex, Rhino5,
Sorare, Paradex,
Rhine,
which is a layer 3.
Many. So all of these systems are using StarkX, which StarkX and Starknet, they share the same prover, right? So the same validity proof is used to secure both systems. Just StarkX is permission, while Starknet is permissionless.
So this is not a new technology at all. Well, in terms of crypto ecosystem, right?
Right, and the best part about Starknet, in my opinion, is that there's no need for trusted setup, because that is a property of ZK Starks that ZK Snacks don't have. So higher security guarantees, in my opinion. All right, let's talk about the smart wallets. One of the features, I think Omar and I were actually fascinated by this for still today, but I think at the beginning, we're actually doing a lot of research in that area. So what is a smart wallet? Smart wallet is a wallet that allows you things like, for example, sign transactions with Touch ID or Face ID. These are the terms that you see in Apple, but other devices, Android, they also have different terminology for the same thing. And it actually allows you to execute multiple operations in a single transaction, right? This is the multi-call that I explained before. On Starknet, every wallet, it is a smart wallet, right? There are no externally owned accounts like on Ethereum. That's important to keep in mind. Every single wallet is a smart wallet that uses account abstraction, and it has a smart contract on, okay? So the two main providers for wallets are Argent and Bravos. So if you want to create a wallet on Starknet, choose one of them, and they both will create you these smart wallets. Now, what do I mean by multi-call and what's the benefit? Sometimes an action requires multiple steps, right? Or multiple user operations. And if you think, for example, an AMM, usually you have to approve spending tokens, and then you have to actually do the swap. And that's normally like two different transactions. You will think that because you send two transactions to belong to the same sequence, that maybe they actually get included in the same block, in the same order that you define them. But that's not guaranteed, right? It might very well happen that they get included in the same block, but maybe in a different order with some transactions in the middle. Or it could be that they actually get included in different blocks altogether. What that opens the door is for what's called MEV extraction, right? There's different types of attacks that a transaction can be put in the middle, even in the middle or before and after, try to steal a little bit of your money, maybe a lot of your money. Now, when you have something like multi-call, like in the case on a Starknet, when you have these complex interactions, you can actually send them as a single transaction, right? Let's say that we have the same two operations as before for the AMM to approve and to swap. Now you can actually send them as a bundle. And the bundle, actually, because it's a single transaction, they actually get included in the same block and in the same sequence. Finding. No longer you have the risk of the transactions being added to different blocks, and you reduce the footprint for MEV extraction, among benefits on, for example, less overhead for the transactions, which makes it cheaper as well, because now you don't have to verify signature of multiple transactions just for a single one, among other things.
There's a question regarding whether there is a faucet for Sepolia yet. As far as I know, there's not like a front end right now.
There's not yet,
right,
no.
Dave? Yeah.
No.
But you can reach your Sepolia resources. I share with you through the chat the addresses where you can bridge your Sepolia tokens from layer 1 to layer 2, but using directly the smart contract Etherscan. Not that hard, but you will need to go through this. We don't have the front end yet, but we will have it.
Yeah, for now, I think Gurley is still the place to go as a testnet. It will be supported for a couple more months, but eventually we're going to have to switch all to Sepolia. But we're in the middle to try to enable support for Sepolia on the bridge and for the faucet as well, but not quite there yet. Pablo is asking, that's really great to know. What about if I use this functionality for financial operations and I don't want my strategy to be reverse engineered? Is anything I can do to protect the strategy when putting all the transactions together? Well, the thing is, Starknet is completely an open ledger, right? It's transparent. It's not a privacy preserving protocol. So if you rely on complete privacy, no. But you can minimize MEV extraction by bundled transactions and get cheaper transactions for that as well. Yeah. So I mentioned that smart wallets are possible thanks to a feature that's called account abstraction. And account abstraction, when you go to the technical terms, is basically the decoupling of the signer versus the account. So the signer is the device that actually signs transactions and identifies the user through a private key. Now, the account is a smart contract that's available on Starknet, and every person that has a smart wallet will have an associated smart contract just for them. The account is the thing that holds the assets, actually, and is the thing that verifies the signature of your transactions, right? And that is programmable. You can define what's the logic to verify the signature, which gives you a ton of flexibility about how do you want to sign transactions. And also, it allows you to execute multiple transactions or multiple user operations as a single transaction with a feature called multi-call. To see it, account abstraction in practice and at a high level, So if you have a wallet on your phone, typically the signer is going to be a system in your smartphone, usually like the secure enclave if you have an Apple, or they have different names on different devices. And then you will have an account contract on a Starknet, right? Every user will have a signer, and every user will have its own account contract. If you have 3 different smart wallets, you have 3 different account contract and 3 different, could be the same signer actually, but 3 different account contract. Now this is a smart contract. I call it account contract just because they need to comply with a specific interface to be considered an account contract. That is defined in the SNP 6, and the SNP is the Starknet Improvement Proposal, similar to the EIPs on Ethereum. And it needs to have those three functions at least: the execute, where we actually do the multi-call; the validate, where we verify transaction signature; and is the valid signature, which is the one used by Web3 applications to also verify signatures, mostly used for authentication for Web3 apps. Anonymous asks, do you also have Paymaster enabled on a Starknet? Not yet, but it's coming. So when you want to actually interact with some smart contract, I'm going to call it the Starknet smart contract, what's going to happen is that you're going to sign a transaction, and that transaction is going to go through your account contract, and it is your account contract who actually does the communication with the target smart contract, right? So basically, you have some proxy in the middle that belongs to you, but it's a smart contract to smart contract communication. On Starknet, there are no EOAs. Everything is a smart wallet. I mentioned that one of the superpowers is that signature verification is actually programmable at the account level. And that is super powerful because it enables features like, for example, obviously the more basic one is have a single signer, or having multiple signers, which we normally know as a multi-sig. So a multi-sig on Starknet is not that different from a regular smart wallet. It's just a smart wallet configured to have different signers to be valid with some logic about when to actually consider a transaction to be all the complete signatures. You can also enable a hardware signer. In this case, will mean using the secure enclave of your phone to sign transactions, which will make your phone very similar to a cold wallet. You also can have social recovery, which instead of the seed phrase, you can actually have guardians, like some friends and family, that can attest about your identity and allow you to have a different signer in case you lose your signer. Or having things like session keys, for example. If you are into gaming, that's very useful, that you allow temporarily a third-party key to control your account, maybe for a specific ERC20 token, for a specific market balance, in a way that you can play now a Web3 game, and you don't have to sign transactions constantly. You delegate that to the session key for a limited time, for a limited. And there are many more cases. This is just the more that comes to mind.
I have a comment. An alternative name to account abstraction is validation abstraction, because all these validation steps can be implemented using account abstraction. It's a generalization of the way you sign your transactions. This allows for smart wallets. So it's also an interesting name to take into mind. And I think this is very, very powerful, and something that is also relevant is the capacity to create two-factor authentication, three-factor authentication, which is a normal step when you have your Instagram account, your Facebook account, any Web2 account has two-factor authentication. We know it more than ever with Twitter right now. But also now you can enforce that in your crypto wallets, which is very, very useful and also very relevant for the user experience of the masses.
So this is why Omar and I were so fascinated about this.
I think it's a requirement, right? It's a requirement for the future. I think it's a requirement for the future of crypto.
Yeah, I mean, Ethereum just released that as well on layer 1. The challenge on Ethereum is that now you have a lot of different types of wallets that Web3 apps needs to be aware of, right? Like EOAs, the smart contract wallets, now account abstraction, which creates challenges on its own. Starknet has a blank slate, so we were able to, from the beginning, just apply account abstraction all over the place. There are 3 types of elliptic curves natively supported by Cairo. We have the Stark-friendly elliptic curve, which is like the native elliptic curve for Cairo. In this case, it will be the most efficient one. It also supports the Ethereum elliptic curve. If you want to sign transactions, for example, with your ledger for your smart wallet, that's technically possible. And it also supports the standard elliptic curve, which is the one that normally your smartphone will be using in the secure enclave. I keep talking about secure enclave. Maybe this image will be easier to explain what that is. Every smartphone these days have 2 different systems. It has the shared system, where basically that's where all your apps lives, and they have a shared CPU and shared memory that all the apps use. But then they have a secure enclave, and basically it has a dedicated processor and dedicated memory for things like, for example, cryptography, managing different type of private keys, signing transactions with a specific hardware using this standard elliptic curve. And that is what things like in the case of Apple, Keychain, Touch ID, and Face ID actually use. So it has a much higher level of security than the shared system. So that's what I'm saying, that with account abstraction, smart wallets, when you have a hardware signer enabled, you have a security guarantee very closely matching that of something like a ledger, like a hardware cold wallet, because you're using the secure enclave of your phone, which is custom made for this type of. Now, secure enclave is the name for Apple, but if you have a Google or a Pixel phone, it's called Titan M. If you have a Samsung phone, it's called Knox. And if you have any other phone that has an ARM chip, it's called Trust Zone. So each of these vendors, they have that implementation. So pretty much every modern smartphone, they have that secure subsystem.
Yeah, this is state-of-the-art security. So it's the same security that secures your credit cards when you make payments with your phone.
Yeah.
So we are at that level right now.
Manuel is asking, hardware signers, can this aid me integrate Starknet with IoT devices? Absolutely, yes.
Yep.
It also applies for laptops. Laptops also have the same secure subsystem.
What? Which one?
Laptops.
Oh.
Most laptops will have a secure subsystem as well. Okay, so in summary, smart wallets. First of all, they offer a much better UX than regular wallets. You have things like multi-call, hardware signer, social recovery, session keys. All of this is enabled thanks to account abstraction, which allows you to decouple the signer from the account. And an account is just a smart contract that has a specific interface as defined by the snipper. And it supports signing transactions with different types of elliptic curves and follow programmable logic that you define on your account contract. And on Starknet, every single wallet is a smart wallet. There are no EOAs. Carlos is asking, why is people going crazy about the Solana phone when they make their own phone on AA wallet with Starknet? I don't know if that's a joke or
I think he's serious, David. Don't laugh.
I mean, you
Every
can have it
phone
done now. If you install Bravos, for example, you can today just enable hardware signer and will use the secure enclave of your phone.
Every phone is a Starknet phone with Bravos, with Argents.
Yeah, you don't have to buy a new phone specific for crypto operations. Just your normal phone will support.
Which is amazing, right? Which is democratizing crypto.
Oh, that's what he meant. Like, why do you need a special phone? Like, why is Solana trying to create a special phone when you can actually have any phone doing that today? Runs into advertise their phone. Maybe the Starknet phone. Maybe one day we will have it. All right. I want to do a simple exercise here with you. Basically, what I want to show you is how to install a browser wallet. In this case, I'm gonna use Argent as an example. You can also use Bravos if you want. Then I'm gonna create an account on Girly, which is the testnet. In the future will be Sepolia, but for now I'm just gonna stick to Girly. I'm gonna fund this smart wallet using the faucet. I'm gonna then deploy the account, because remember, the account is a smart contract that needs to be deployed. I'm gonna check the account source code just to see that this interface that I mentioned before, that it actually exists there. And I'm gonna use it to interact with a simple counter smart contract, and maybe I can show you the transaction life cycle. Something else. All right, so I'm gonna go to the store extension, and I'm gonna search for Argent. Argent X, it's the name. You can either use Argent X, which I'm gonna add as an extension, or you could use Bravos, the other option that you have, right? I'm gonna stick to Argent for now. I'm gonna create a new wallet, and yes, I understand. Continue. New password. I'm just gonna remove this wallet after, so I'm just gonna give. Gonna let me this simple password. Oh my god. I want security. I just want an example. All right, it's apparently created. So let's take a look. You want me to save the query phrase? Yes, you should. I don't care. Just an example here. I'm gonna move to testnet, so I don't spend any real money. I'm gonna create an account. I'm gonna use a standard account. You can have, for example, Argent support multi-sig, as I mentioned. So here you have it. it's created. The account contract, the smart contract behind this is not yet deployed. What Argent does is that it's gonna wait until you send your first transaction, and at that point, it's gonna also deploy. Like first, it's gonna deploy the account contract, and right away, it's gonna execute your transaction, right? So they do that just to simplify the UX for people. So let's see. Let's gonna add some funds, and for that, I'm gonna use the faucet, right? So, oh look, the Stark token is now enabled here. Oh, fancy. Let's do. Fire hydrant. What am I doing this? I need to provide the address of my wallet, which is this one. Put it here. Give me some test. Motorcycle. Oh my god, so many. Oh my god, forever. All right, finally, send request. All right, so the faucet is sending me a bit of test ETH, which we can track here. We can see that this transfer went from
It already achieved L2 finality very fast.
yeah, already see accepted on L2. It will take a long time to get accepted on L1, as I mentioned, about 2 hours more or less. But now it should be now available here. Should be.
You need to update it.
There you go. Yeah, 0.002 ETH, right? So now what I want to do is to take a look at this the account contract behind this. So let me see if I can copy this and I go to start scan. I think it's this block explorer. They take a while to index the blockchain. So even though the transaction might be final and all that, it's not completely synced. So let me try Voyager to see if they actually sync a little bit faster yet. Oh, you know what? That's because they're waiting for me to send the first transaction to actually deploy the account contract, and I haven't done it yet, so the account contract is not deployed. So let me create another account just as a target to send funds. I'm just gonna copy this address, and I'm gonna send some funds here, right, from account 1 to account 2. Say send, use this address. And
but why are you doing this? Oh.
Yeah, because Argent doesn't deploy the account contract unless you send your first transaction.
Oh,
it's different from Bravos. So I'm gonna confirm the transaction, and that should be it. Space the transfer happened. Let me try again. Should I be able to see it? Okay, now it exists. So we can see that it first happened the deploy account. This is when the account contract will deploy, and then the actual transaction that I want to execute, the sending the tokens. If I see the code, I don't know if you're gonna show it to me. But you can see the ABI, and you can see if I increase the font size. Here's the validate function, and you will be able to find also the execute here. Somewhere here, the execute, and you get the meaning, right? So it's actually following the standard that I mentioned before. Cool. Finally, I want to use it to interact with a smart contract, something very simple. This is just a counter smart contract. So basically, you can just say, I can read from the smart contract, just a counter. So right now it should be 1, unless someone is modifying. Yes, just 1 decimal. I can connect the wallet and then close them. Is this the one I'm using? I think I closed the wrong. Oh yeah, right. Now I'm connected. Let me close the windows. Now I'm gonna modify, I'm gonna write. I'm gonna call this increase counter, transact. It's gonna send a transaction, and you see the contract interaction happening here. Let's see. Yeah. Right. But again, it's gonna take a while for the block explorer to actually re-index this smart contract and get the new number. So, oh, happened fast. So now it's 2. So we just installed the Argent browser extension. We created a new smart contract. We funded from. In this case, I just sent a test transaction ETH just to force the deployment of smart contract. You don't have to. You just can just interact with the smart contract. It will deploy it for you, and then just interact with some simple counter smart contract to show you how it works and how you can use it in connection with a block explorer. We go into the last section of today's session 1, which is an introduction to the architecture of Starknet. We're going to go deeper into architecture next week, but I want to just give you the basics now. So Cairo, you know that it's a provable programming language, syntax similar to Rust. We talked about that before. But what we didn't talk until now is that when you compile Cairo, you don't compile it directly to the Cairo VM bytecode. You actually compile to an intermediate language that is called Sierra. And Sierra stands for Safe Intermediate Representation. And the reason that intermediate language exists is twofold. It allows to keep improving Cairo as a language without having to modify the compiler too much, or at least the compiler that goes from Sierra to the Cairo VM to the bytecode. But more importantly, it allows to create what's called safe Cairo assembly, right? Because we call it safe Cairo assembly is that we want to make sure that when a transaction fails, right, which sometimes happens also in Ethereum, we want to make sure that we actually can include that failed transaction in the block, which, believe it or not, before with Cairo 0 or before Sierra was not possible. And this is a problem because in the past, when a transaction failed, it was not possible to include it in a block. It was not possible to prove, which means that the sequencer didn't get compensated for that work. So that was a potential denial of service vector that we also closed thanks to having Sierra and this feature that it actually creates safe Cairo assembly, and safe in the way that it's able to handle gracefully failed transactions in a way that it can be reverted and included into blocks. Logan asks, is Sierra similar to Air or RISC? No. When you think about RISCs and Air, it's more like a low-level bytecode that is a Cairo assembly, right? Sierra is like an intermediate step between the high-level Cairo and that low-level bytecode. All right. So we go back to our story, right? When we say, you can send for the space exploration, you send your code to the rival country, they give you back the result plus the proof. But how does it actually work under the hood? What modules will be involved? So on your side, you will have your laptop or your computer that you control, and that's where you will have your Cairo program, right? This is the program your engineers created to find what is the best launch window and the best trajectory for your spacecraft. First step will be to compile the Cairo program to Sierra, right? I mentioned this intermediate language. And now is this Sierra code, that's the one that you actually will send to the rival country for the supercomputer. And now on their side, they actually now want to compile to Cairo assembly, or really the safe Cairo assembly. And the Cairo assembly is the bytecode that you can actually execute on the Cairo virtual machine, right? Out of the result of the executing this code, you will get what's called an execution trace that you can send to a prover. That will be a module in the supercomputer. And obviously the prover is the one that's going to give you the validity proof that you can actually now verify on your computer to have certainty that no one tampered with the execution, but also will give you the result, right? So the prover does the actual calculation, but also creates the validity proof for you to verify. So those are the modules that will be taking place in this example. But now if we actually evolve this towards actually the modules for Starknet, at least a first iteration, and in the Starknet, it'll start with you, with your laptop. That's where you have your Cairo program. And again, as before, you will compile to Sierra. Now when you send it, you don't send it to a big computer called the sequencer, right? That's one computer that is part of Starknet. So the sequencer gets the Sierra code, it will compile to Cairo assembly, and it will run it in the Cairo VM, right? So these modules or these steps happens at the sequencer. And then there's another computer that we call Sharp, and start for shared prover, that actually has the prover module, right? So the trace of the execution is sent to the prover, to Sharp, and Sharp is the one that will give you the result, but also will send the validity proof, in this case to Ethereum. So it's actually sending a transaction on Ethereum with the proof towards a specific Solidity smart contract known as the verifier. So in a nutshell, these are the modules involved in Starknet. Paul is asking, where are the sequencer and the Sharp located? I believe right now they're just on AWS. Eventually, the goal is to decentralize both layers, sequencer and the prover. But for now, we have a single huge computer for both of them. Now, obviously, this is an oversimplified version of the architecture for multiple reasons. First of all, in the case of a Starknet, you don't have a vanilla Cairo program. You actually have a smart contract, right? And before you can execute a smart contract, you actually have to declare it, and then you will need to deploy it. Only then you can actually interact with the smart contract to do some calculations or some computation. And the way you interact with the Starknet is actually via transactions. And transactions, they have to be signed. So first, you will have to declare the code. And declaring, start with your Cairo smart contract, right? On your side, on your laptop, the one that you create. You will compile it to Sierra on your computer. And then you will use your wallet, right, to create a transaction for a Starknet. And that's a transaction called the declare transaction. The declare transaction will send the Sierra code to the sequencer mempool. And the mempool or the sequencer will take the Sierra code, and on its side is going to do the compilation to Cairo assembly. Now, here, there's a disconnection between that execution, that compilation, and the prover. And there's a problem here. And the problem is that the Cairo compiler is written in Rust, right? But because it's written in Rust, it means that the compilation itself cannot be proven as of today. Now, the long-term solution will be to write the Cairo compiler in Cairo, very, very meta. But if we do that, it means that even the compilation of a smart contract will be able to be proven, which is not the case right now. So the stopgap solution at the moment will be that when you declare a new code, and declare basically means just, I'm going to register a new smart contract on the network, just the code. Not only will have to provide the Sierra code, but on your side, on your laptop, you will have to also compile to the Cairo assembly and get the hash of that program, right? Of that compile program. So when you declare the code, you also provide the hash of the Cairo assembly. You will let then the sequencer will do the recompilation from Sierra to Cairo as before, but now you need to make sure that those hashes will need to be the same, right? When you compile to Cairo assembly on your side and when the sequencer compiles to Cairo assembly, just to make sure that the sequencer is not cheating, you need to make sure that those hashes will be the same. So if we go back to deploying the code, which is just to register a new code for a smart contract, same steps, right? You compile to Sierra, but now you will also have to compile from Sierra to Cairo assembly on your side. And the transaction that you send, the declare transaction, not only will have the Sierra code, it will also have the hash of the Cairo assembly code that you will send to the sequencer. We'll get it in the mempool. The sequencer will take the Sierra code, will do the compilation by itself independently to Cairo assembly. But now, you know that if the sequencer maybe tries to cheat, creating a fake compilation Cairo assembly or a fake compiled Cairo assembly, you will know because the hash is not going to match. The hash that you send versus the hash of the code of the Cairo assembly derived from the sequencer. So that is a stopgap solution until the Cairo compiler is actually written in Cairo. All right, so that takes care of the process of declaring. And declaring is just register new code on a Starknet. It's not yet ready to be used because to that, you will have to deploy. The question is, what's the difference between declaring and deploying a smart contract? So declaring a smart contract only registers the code on a Starknet. A declared smart contract is known as a contract class. A contract class is identified by its class hash, right? So the sequencer assigns a class hash for any new declared smart contract or contract class. Contract classes are pure code. They don't have internal storage. It's just the logic, it's just the code. Now, contract instances can be derived from a contract class, similar to the OOP concept. So from one contract class that is identified from a class hash, you can derive one or many instances just by executing the constructor of your code, of your smart contract, and assigning the actual storage. Because now the contract instances, they have storage. They are the smart contract that you normally interact with. And each of these instances is uniquely identified because it will have a different address on Starknet. So this is key to understand. Declaring and deploying. You first have to declare, then you have to deploy an instance of that code that you declare. And now you can actually invoke methods on the smart contract because the deployed version, it will be the thing that we normally call the smart contract that we interact with because it has storage. Now, there's a thing called the universal deployer on Starknet. And that thing is it's a smart contract on a Starknet that its only purpose is to deploy other smart contracts, which means that there's not a deploy transaction on Starknet. You use another smart contract as a proxy to deploy your smart contract. So this universal deployer has only one selector, only one function called the deploy contract. That when you call it, you have to provide the class hash, which code that you're going to use as a blueprint, and then the constructor arguments of these blueprints. So you can derive the contract instance. Internally, it uses a specific syscall called deploy. It's not a transaction, it's just a syscall in the smart contract. This universal deployer is created as a public good, was created by Open Zeppelin as a public good on Starknet, so you can deploy your smart contracts with it. This is a fairly old smart contract, so it's still written in Cairo 0. It's not yet written in Cairo 1. And if you go to, you can see it. If you go to StarkScan, let me go to mainnet in this case. If you go to, I think the address, where do I see this? I think the address book. You can find the Open Zeppelin Universal Deployer. If you see the code, you can see this is Cairo 0. This is the old Cairo. This is the one that Omar and I had to learn when we started. Cairo 1 is a much nicer language. But you can see here that the only function that it has is a deploy contract that is expecting the class hash, which uniquely identifies a declared code. And then this is the constructor arguments of your declared. And internally, it uses the deploy transaction, the deploy syscall here, right? So it does the deployment for you. Okay, so now, because now we know that we have a smart contract classes and a smart contract instances, there are two things that you. So when you declare a smart contract, obviously you create a contract class. And as I mentioned before, through the universal deployer, you can create multiple instances, right? But the other way that you can use a contract class is by create a library. So now maybe you don't use it to derive other smart contracts. You only use it for its logic. And you can execute that logic in the context of the smart contract which is calling it using another syscall called library call, which is similar only to that delegate call. I think it's very similar because this is pure logic. This contract class doesn't have storage, but the logic is useful on its own as a library. So now when you want to deploy a smart contract that has been previously declared, you will send what's called the invoke transaction. And the invoke transaction will have the address of the universal deployer that I just showed you the code. You will have to define the class hash and the constructor arguments. And when it gets to the mempool, obviously, what it gets executed in the Cairo VM is the constructor of your smart contract. And that's the thing that actually gets sent to Shard for proving. And as before, that proof sent to layer 1. And as a result, the answer that you get is the new address of your deployed smart contract. So now once deployed, you can actually use it. Use it in other terms, it's called invoke. And that uses the invoke transaction. So in this case, you will have to define, okay, which smart contract address you want to interact with, which function in particular you want to use, what are the arguments that this function expects. It will get to the mempool. Now in the Cairo VM, you execute that function, right? That's what the transaction is trying to do. And the output of the whole thing is the result of the execution, like the new state of the network, and levelability proof sent to layer 1. Question, can smart contracts deploy other smart contracts in Starknet? Yes, that's what the universal deployer does. It's a smart contract that deploys other smart contracts by using the deploy syscall. You can create your own if you want, but the same smart contract created by Open Zeppelin is used by all of us. You can use it too, and you don't have to reinvent the wheel. So to summarize, Cairo compiles to Sierra, which is this intermediate language. Sierra compiles to safe Cairo assembly, which allows for transactions to be reverted here. Declaring creates a contract class, and contract instances are derived from contract classes. Also recall that contract classes, they don't have storage. They're pure code. It's just a way to register new code on the network. Instances are the ones that actually have storage, and that's the one that you normally consider to be the smart contract with. A contract class can also be used as a library with this specific syscall. And Cairo assembly hash is used to prove compilation, just because the Cairo compiler is written in Rust, not in Cairo. And deploying a smart contract requires interfacing with a universal deployer, also a smart contract on Starknet. And we saw two transaction types, declare and invoke. And invoke is used for deploying and for interacting with a smart contract. All right, that's the end of today's session. Thank you very much for participating. So we'll see you guys next week, same day of the week, same time. Hopefully a much more interesting class, because we're going to go deep into architecture and proof recursion, which are very interesting topics as well. Thank you, Omar. Thank you all.
Thank
See you
you,
soon.
David.